Well, as the title says, we're going to talk about lessons unlearned, and these are the lessons we unlearned during the 5.5 years we were an independent company, Flarion Technologies, and we were developing a new wide area network technology. Now, I noticed at the picture that it shows these are not supposed to be targets. They're supposed to show wireless devices, actually. And we were counting the wireless devices people carry today. It exceeds that number by a little bit. I just counted 5. I think I'm down to 4. 1, 2, 3, 4. And there was this remote that didn't work. So anyway, wireless, it's pervasive. It's changing the way we live. So I'm going to talk not about all the ways it's changing the world, but more about technology. So there's a little bit of history about the title itself. Actually, I don't know if many of you might know Tom Richardson. He was our chief scientist at Flarion. He's still with Qualcomm Flarion Technologies. He came up with the title, and precisely for this reason. He thought it attracts more people than just lessons learned. And it actually, I'll tell you why we call it lessons unlearned later. I've given this talk many times now. I was thinking of retiring it. I've given it so many times. But I think for a university audience, there's actually still, there's stuff here that I think is valuable. At least I think so. So lessons unlearned. So I'm just going to list a few lessons and go into details in several of them. The first lesson we unlearned was all orthogonal bases are equivalent. So people say, oh, TDMA, FDMA, OFDMA, CDMA, they're all basically ways of partitioning the available degrees of freedom into an orthogonal basis functions. Right? So at some level, they are all equivalent. And this is true. At some level, they are all equivalent because you're just basically carving up degrees of freedom in various different basis, various different types of basis functions. But the number of degrees of freedom is specified by basically Nyquist's theorem. You have certain bandwidth for certain time. You have so many degrees of freedom. You can carve them up differently. And CDMA basically creates Walsh functions or other, irregular shaped functions. TDMA separates them in time. FDMA separates them in frequency. OFDM does something somewhat in between, but mostly separates them in frequency. But they're just various ways of doing things, and I think in the talk we'll show that why there are subtle reasons as to why they're not equivalent. Okay, and the reasons are subtle, but nonetheless important. So another lesson we unlearned was that the cellular channel model was that the output of the channel is equal to the channel multiplied by some gain plus some additive noise. Now, when I use that, I actually, what I'm trying to say here holds even if I have a channel with memory and fading. So that's not the point I'm trying to make. But it turns out that this is actually an incomplete description of the wireless channel, especially as it applies to wireless wide area network systems, and especially as it applies to wireless wide area data network systems, because the goal with second generation voice systems was to do 8 kilobits per second everywhere reliably. Okay. The goal with data is a little different. Nobody wants to do 8 kilobits. People want to do as high a data rate as they can, and so therefore want to maximize the SNR. If you only have to do 8 kilobits per second, you don't need very high SNRs, especially if you have a megahertz of bandwidth and you want to do 8 kilobits per second. You never have to operate in high SNR regime. But for data, you basically want the SNR to be as high as possible. And we'll see that when that is the case, this is an insufficient description of the wireless channel. Okay. Another lesson unlearned was that OFDM is a physical layer. I should say, yeah, it does say only a physical layer technology. It is a physical layer technology, but it turns out that in wireless systems, physical layer isn't the only layer that you're interested in designing. There's a whole lot of layers that sit on top of the physical layer. And having the best physical layer design does not necessarily lead to the best wireless system, because it's the weakest link in this chain that actually dictates the performance of the whole system. Okay? So while it's important to have a good physical layer, it's also important to optimize across everything that sits on top of the physical layer. And all technologies are not equal from the point of view of how they interface with the higher layers of the system. Right? It turns out that OFDM as a physical layer technology actually makes it relatively easier. The job at the higher layers actually becomes easier. So it's actually a little more than just a physical layer technology. Now, another lesson we unlearned was that TDM in the downlink is optimal. So in the downlink, you can always divide the channel in chunks of time, and you can do different uses at different points in time. Since there's only one transmitter in the downlink, it was believed that it is optimal. Actually, it isn't optimal. And for wireless data, wide area network data systems, reuse 1, which is very prevalent right now in the wireless world in CDMA systems, is also not the most efficient way of designing things. Reuse 1 is not the best. It was almost, when we started, it was almost a sort of a God-given reality that every system has to be reuse 1, and that's the best way to do things. It turns out that's actually not true. However, in this talk, we're only going to talk about these 3 points. We won't have time to cover these 2. They're actually very, very interesting things in themselves, the fact that TDM isn't optimal. But we won't get into that today. Now, a lot of people here might know what OFDM is. It basically takes your available resource and divide. So OFDM is signaling on a tone. So if you have a tone, there are 2 independent parameters of the tone that you can actually signal on: the phase and the amplitude. So you can signal 2 real numbers on a tone. However, a tone is of infinite duration. So it doesn't, you can only put 2 numbers on there, and you have to wait a long time. So a tone by itself is not adequate. You have to somehow find a way of repeatedly putting numbers on the tone, so to actually communicate something meaningful. So you have to somehow limit the tone in time. Okay. So OFDM is a way of transmitting on various tones that are also limited in time. Okay. And there are multiples of a fundamental tone. Okay. And if you don't go through a channel, you can limit these tones in time, and you can actually recover these at the receiver, because these tones, if they're multiple of the same fundamental tone, are orthogonal signals. So when you're looking for one, you don't see any interference from the others. So if you're looking for a specific tone to see what the amplitude or what the phase of that tone was, and you build a mesh filter to that tone, it doesn't see any contribution from any of the other tones. So the tones separate at the receiver very well, and when you're looking for one, you don't see any interference from the other, so you can use the tones to communicate. That is in case the channel, there's no channel. Channel is a unity channel. However, if the channel has any delay spread or memory, then if you transmit a tone, you will see interference from other tones when you try to receive the tone. Except if the channel memory is a finite duration, right? So let's say you don't know in the wireless world, when you transmit something, you don't know what channel you're going to encounter, because the transmitter has no knowledge, and different transmissions encounter different channels. However, if you know that with very high probability, no matter what channel nature picks for you, the memory of the channel is going to be limited in time. So in other words, if you put an impulse out, the response to that impulse from the channel dies down in certain time tau. Then you can, and if that happens, then you can have this OFDM system work very well without interference at the receiver, just by adding a cyclic prefix to each symbol. So you extend the duration of each tone by the amount of the maximum memory of the channel. So if it's tau seconds, then you transmit not just a fundamental period of the tone, but also an additional tau seconds of the same tone. And you do that for every tone. So basically, you cyclically repeat every symbol that you transmit, and you transmit it for tau extra seconds, tau being the maximum memory of the channel you're likely to encounter. Under that condition, at the receiver, this tau seconds acts like a guard band now, right? After you've observed the tone for tau seconds, whatever you observe after that is now free of any memory effects of the channel, because any memory effect has died down in the first tau second. So if you did that, now then the OFDM systems again can be, excuse me, wireless devices, can be made such that at the receiver there is no interference from other tones. When you're listening to one tone to determine what phase and what amplitude it has, and you build a receiver to do that, which could be an FFT, you do not see interference from any other tone. In other words, that at the receiver, these signals that you use to transmit on are orthogonal when they're received. So you basically, you can pick out the tone that you're interested in, get the information off it. You do not see any interference at the receiver from all the other tones. So this is a special property of OFDM systems, that irrespective of what channel, so the transmitter doesn't know what channel realization nature gives you, but irrespective of what channel you see, a simple receiver can be made in which you can basically, each tone, you can isolate the information in each tone and they do not interfere with each other. So at the receiver, these tones continue to be orthogonal. Okay. So usually people like to signal orthogonal sequences or orthogonal symbols, so that when you transmit few orthogonal signals, you can sum them up and you transmit them. And typically at the receiver, you would like these signals to stay orthogonal so that you can receive each one of them without seeing any interference from one to the other. Now, in OFDM systems, the signals you pick obviously at the transmitter are orthogonal, but they have a special property that independent of what channel they go through, and the receiver doesn't even have to have technically knowledge of the channel in order to demodulate, but they stay orthogonal at the receiver, which is where it's more important to be orthogonal, so that you can easily decode the information without needing to do any special things. Okay. Now, if you take the example of CDMA, the wash codes are orthogonal at the transmitter, right? However, if they go through any multipath channel, they are not orthogonal at the receiver, right? So you could make them orthogonal at the receiver by putting an equalizer, for instance. If the SNR is low, it turns out that the rake receiver is the MMS equalizer, but it doesn't. High SNR, that would not be the case. You'd have to build a proper MMS equalizer, which of course presents its own challenges because the wireless channel changes can change very frequently, and to keep the equalizer trained. However, there are other reasons. So even if you start with, excuse me, I have to find a way to kill that. If I open it right now, it will answer the calls. So at the receiver, the signals stay orthogonal independent of the channel realization. That's in any orthogonal transmitter, you can eventually orthogonalize the received signal by putting a certain equalizer that undoes the effect of the channel. Okay. If you know the channel, you can undo the effect of the channel, provided the channel doesn't have nulls, you can undo the effect, and then you're back to this situation. But there is a fundamental difference which I will come to later. So this is, most of you probably know this is how OFDM stays orthogonal, because at the points at which you measure these tones, that you see contribution only from one tone, and all the other tones in frequency are going through zero at that point, so they're non-interfering. If you sample in frequency exactly at the right spots, you get only information from a single tone in each of the samples. Okay. So the conventional wisdom is at some level all orthogonal basis functions are equivalent. You can use CDMA, you can use TDM, you can use FDM, you can use OFDM. At some level, they're all the same. But OFDM is a little special. OFDM does use tones to communicate, and we know that for all linear systems, tones form eigenfunctions. So the OFDM basis is really an eigenbasis for any linear system. That makes it somewhat nature's chosen basis, and makes it somewhat special. So one of the ways it's special is that orthogonality is actually preserved under multipath delay spread, provided you know that the channel memory is finite and you've accounted for that in cyclic prefix. The actual realization of the channel is not important as long as the system is linear. That is, the channel isn't changing with time. The received signals stay orthogonal. Okay. So we'll also talk about the fact that this is an eigenbasis. turns out to be advantageous not just in communicating, but in doing a lot of other things that need to be done in a wireless system. So when you design a wireless system, the ultimate function of the wireless system is to enable users to communicate with each other. However, in making that happen, there's a lot of other things that need to happen in a system which have very little to do with users communicating, but have everything to do with the system functioning. Right? The users need to be able to discover that there's a base station, that there's a service being offered. There's a lot of other things that need to happen to make a wireless system function, in addition to users communicating. Okay? And it turns out that using this sinusoidal functions or eigenbases actually even is helpful even there, not just in actual communication or the communication efficiency of the system. So what OFDM does, typically it takes your available resource, which is plotted, this axis is time, this is tones, and it divides it into a number of these boxes, where each box here represents a single tone for a single symbol duration. Okay, and what orthogonality says is that you can put whatever you put on this box at the receiver doesn't interfere with anything in any other box. You can put something in this box and recover at the receiver without interference. Now, perfect orthogonality exists only in textbooks. Okay, real systems are never perfectly orthogonal. In fact, there is nothing about real systems that's perfect, and there is nothing about real systems that should be perfect. Real systems should be perfect only to the degree where it matters, and no more, because everything comes at a cost. And engineering is all about making the right trade-offs. You never want to put cost in a system if it doesn't give you any return for the cost. That's what engineers do. They engineer systems to make them work just right, not any better than they do, because if better doesn't give you any more value, that is an increased cost, then it, as engineers, it's our responsibility to say that actually would be an improperly engineered system. If it worked better, then it should work. Okay, so what does orthogonality mean then in the real world? Okay. In the real world, we know you put enough power on this box, eventually it shows up in other boxes, right? The most orthogonal systems we know are really FTM systems, because you can build passive filters that can contain energy in a band. They're not perfect, they're not ideal, but they're probably, if you really wanted to make really as orthogonal as we can, FTM systems would probably be more orthogonal than OFDM systems. CDMA is not orthogonal, relatively speaking, because slight amount of channel delay spread will cause degrees of freedom to mix with each other. OFDM is somewhere in the middle. OFDM is what I call 35 dB. It's easy to engineer OFDM systems that are 35 dB orthogonal. What does that mean? 35 dB is a factor of 4,000, right? Which means you can put 4,000 times more energy on one of these degrees of freedom than the other, and still not have it bother the other degrees of freedom. Okay, this is easy to do. You can also engineer OFDM systems to do higher than 35 dB orthogonality, but the gains of doing that are not there actually. You don't gain any capacity in the system by doing so. So big engineers, a good trade-off is around 35 dB, and it's easy to construct OFDM systems that under this definition are 35 dB orthogonal, where you can put 4,000 times more energy on some degrees of freedom than the others, and the system still operates because there's not enough mixing. So if you put 4,000 times more energy on this degree of freedom and here, and when you try to decode this one, let's say a tenth of its energy leaked over here, then you really couldn't use this degree of freedom from communication at that point, right? So, but if you have this kind of orthogonality that says even if you put 4,000 times more energy here than here, you could still use this one for communication because it doesn't get bothered by the higher energy you put elsewhere.
When you say you can achieve 35 dB orthogonality, are you referring just to the receiver design? In other words, that's what you can do with existing technology, or are you including the effects of multipath?
I am including the effects of multipath, yes. It's because in OFDM, multipath doesn't doesn't interfere with orthogonality, provided it is contained in some finite duration, and you've counted for that. The actual realization is immaterial. Your degrees of freedom still stay orthogonal. So even if you had a two-path channel, for instance, provided the paths were within tau.
Yeah, I mean, that provided is, of course, an approximation. What I'm wondering is, in practice.
So that when I say it is possible easily to design 35 dB, what that means is, in practice, most channels are such that that it is possible to put a reasonable cyclic prefix or guard band and make sure that the energy is significantly. So what happens is, if a path arrives early, let's say, and another path from the same source arrives a few microseconds later, 1 microsecond means 5,000 more feet of travel in space, right? So if it arrives, let's say, 10 microseconds later, it has traveled 50,000 more feet, right? So the chances that the second path has any significant energy compared to the first one go down significantly, right? So chances are that under those conditions, if a path comes after 10 and let's say you provide it for 10 microsecond cyclic prefix, that the second path or third path arrives after 10 microsecond has enough energy for you to worry about this is very small. Okay, so 35 dB is easy to engineer because for reasonable cyclic prefix, it's easy to make sure that this doesn't happen very often. That's what it means. So of course, anytime you want to increase this, a lot of things will come into play. You may have to increase your cyclic prefix to make sure that all the paths die significantly. You have to have more linear circuits and stuff, and it's going to be a cost. So you don't want to incur the cost if there is no reason to do so. It turns out that all the gains you're going to get from the system, 35 dB is enough for that. After that, there is no significant gain in efficiency or anything, but you're going to have a much higher cost. I'm going to move on to channel model. They all seem like very different things, but they're all tied together, and I'll show you later how they are. So as I said before, one of the lessons we unlearned was that this is the wireless channel model, and the conventional wisdom is, and I am actually counting for channels here that have memory and that have fading. That's not the point I'm making. The point I'm making is more related to the additive noise part. Okay. Now, the conventional wisdom is this is the right channel model. Okay. And it may be, but not completely. And there's a fundamental reason that this, for wireless systems, is not the right channel model. Now, so we all talk about multipath channels, right? And we can debate about whether two-path channel, since we all know that the wireless channel is discrete multipath. The question is, how many paths are there? Is it 2 paths, 3 paths? What's the right model? Well, the answer depends on what you want to use the system for. If you want to do 8 kilobits voice in 1 megahertz, 1 path or probably 2 paths is more than sufficient to characterize the channel model, because your SNR is going to be very low. Okay. If, however, for data you want to transmit as much data as you can over a given link. So let's say then that means that if you get 40 dB SNR, you want 40 dB SNR. If you get 50 dB SNR, you want 50 dB SNR. Well, if you want 50 dB SNR, then the answer is different than if you want 5 dB SNR, right? So how many paths does a wireless channel model have depends on how deep you want to look. Okay. Because what happens is, if you want 5 dB SNR, then you're only interested basically in paths that are of significant energy. So there is a path with maximum energy. Let's say you get a path with certain energy. If there is another path that arrives that has 30 dB less energy than that, and you're only interested in 5 dB SNR, then that path is of no consequence. You say it's a single path model at that point, because the second path is 20 dB or 30 dB less, and I am only interested in 5 dB SNR. So then the answer is it's a one path model. However, if you want 40 dB SNR, then you have to account for all the paths that are within about 50 dB of your dominant path. Because if you don't account for them, then your SNR can never be, if there are 10 of them and there are 50 dB and you didn't account for them, that limits your SNR, right? So how many paths you take in a model depends on how deep you want to look, because nature gives you infinite number of paths at various power levels. Of course, you don't want to model all of them. You probably cannot, but you want to model enough that actually matter. So the channel model actually, even from a number of paths perspective, depends upon what your application is, right? So it's not the same for CDMA doing voice and RFTDM doing data, for instance, or anything else doing data in which you want to use a 2,000 point constellation versus a QPSK constellation. Because for a 2,000 point constellation, you have to account for a lot many more paths, even the ones that have much smaller energies than otherwise. So how many paths the channel has actually depends on what you're trying to do with it. Now, wireless is a very peculiar thing. The propagation difference of a mobile close to a base station, the path propagation loss difference from mobile close to a base station versus a mobile at the edge of coverage could be as high as 80-90 dB. Okay? 80 dB is not a small factor. It's a factor of 100 million. This kind of dynamic range simply doesn't exist in other kinds of systems. It's very specific to wireless systems. And that actually creates interesting effects that are not visible if you don't see across all of this dynamic range. Now clearly, if a mobile is very close to the base station, it's getting so high power that if this was the only channel model that applied, you should see SNRs of 90, 100 dB easily. If, let's say, if thermal noise was the limit, let's say there's only one cell and thermal noise is the limit, okay, the energy you receive close to the base station may be 150 dB higher than the thermal noise easily. So you should see 150 dB SNR. There is no system in which you see 150 dB SNR. If you see 150 dB SNR, you'll have to engineer the system to see it, and no system is engineered, but most systems are engineered far less than that. For instance, with CDMA, you might only see 13 dB SNR, even if you sit right next to the cell. That's because CDMA is limited by the delay spread, if you will, of your pulse shaping filters. So they create delay spread, and they create non-orthogonality, and they create mixing of degrees of freedom, and the SNR, max SNR you're going to see in an unequalized CDMA system might only be 13 dB. Okay. So clearly, even though your signal to noise ratio, signal to thermal noise ratio happens to be 150 dB, your SNR, the way you measure it, it's only 13 dB. This channel model actually does not explain that. So the fact is that this is not the only noise in that model. Okay. Why is the SNR 13 dB? Because a part of your own signal has become noise to you. And it stays 13 dB even if you keep blasting more and more power out of the base station. It does not increase as the power out of your base station increases. It pretty much saturates at 13 dB, because at that point the only noise you're seeing is coming from your own signal. It's coming from an unequalized portion of your own signal, and even if you see more signal, you also see a higher noise level. So you see your SNR saturate. Okay. In this model, the SNR actually doesn't saturate. If you see more signal, you keep seeing more SNR. Okay. There's actually a more fundamental reason also. So in any system, there's going to be some leakage from degrees of freedom which is going to limit you, and that's going to be a signal dependent noise as opposed to a signal independent noise here, and that is actually always going to limit your the max SNR that you can see. In wireless system, that limit in bidirectional network wireless system, that limit is fairly fundamental in the following way: that in wireless system you can never learn the channel precisely. So even if you spend a lot of energy learning the channel, you still cannot learn the channel precisely. And the reason is that the number of degrees of freedom, or the number of independent the number of independent numbers that characterize the channel is growing. Right? As we try to do more and more data, if there are 50 paths, let's say, then and you want to know the channel precisely, you'll have to estimate each of those 50 paths. Otherwise, you cannot know the channel precisely. Okay, so you will have. So if there is a large number of parameters that characterize the channel, you'll have to know them to know the channel precisely. And to know a large number of those parameters, you will have to waste degrees of freedom to estimate them. Right? You cannot estimate 50 parameters from a single pilot. Right? If you need to estimate 50 parameters over a certain time duration, you need to send 50 pilot symbols. The communication we have is moving into a regime where if you want to know the channel precisely, the number of degrees of freedom you need to spend on knowing the channel actually rivals the number of degrees of freedom you have to communicate. Right? So once that happens, you can never know the channel precisely, because you can spend all your degrees of freedom and energy knowing the channel, then you have nothing left to communicate, or you can keep degrees of freedom to communicate, but then you will just have to live with imperfect channel knowledge. Okay? And I'm not saying it's imperfect at 5 dB SNR or something, but as the SNR increases, that sets the limit, because you can never know the channel perfectly, because especially the channel is changing and the number of degrees of freedom required to characterize the channel rivals the number of degrees of freedom you have to communicate. Okay? So you're left with the fundamental problem that you'll never know the channel precisely. Now when you don't know the channel precisely, what happens? Let me see what the next slide is. So when you don't know the channel precisely, and you, let's say, have a CDMA transmission, or even TDM as conventionally done. So you have a TDM transmission, you can build an equalizer, but you cannot perfectly equalize the channel because you don't even know what the channel is. So your equalizer must leave some energy unequalized, because if you don't know the channel, you cannot perfectly equalize it. And this unequalized energy would show up as interference between degrees of freedom, which you can never get rid of. Right? So it will be another source of noise in your system, which is proportional to the signal power. So, and it does not help to, you cannot get any better SNR in that system if you double the signal power, because it will also double the unequalized energy, and that limit you cannot exceed. Okay? So even if you want to equalize the channel and are prepared to build equalizers, there's only so much you can do. Okay? So this is the other subtle point, the difference that we have between OFDM and CDMA. And let me actually say it out right here. In OFDMA, the orthogonality of the degrees of freedom at the receiver does not depend on the knowledge of the channel. Okay. In CDMA, you can make it orthogonal by equalizing it, but you must need to know the channel. And if you don't know the channel, then you can never make it perfectly orthogonal. In OFDMA, you don't need to know the channel. As long as the channel delay spread is contained in the cyclic prefix, it doesn't matter what the channel is, and it doesn't matter whether you know it or you don't know it, your degrees of freedom will not mix. Okay? So this is a fundamental, it's a subtle difference. In principle, you can equalize everything, but if you don't know the channel, then you cannot equalize it. Okay? In OFDM, the special advantage is that it doesn't matter. You don't need to know the channel. Okay? Your degrees of freedom just don't mix, so there's no unmixing that you need to do. And the fact that they don't mix actually doesn't depend on the fact that you know the channel or don't know the channel. That's a fundamental difference.
In practice, how much does the Doppler effect change the 35 dB kind of orthogonality?
Well, Doppler is something you have to manage in the design of the system. So you have to say, okay, what are you designing the system for? What are the maximum speeds? There's lots of freedom here in picking things, right? The intertone spacing is picked to make sure that Doppler does not, the max Doppler you're going to see in the system does. So that's just a part of the trade-off you make. You set a target for a certain speed that you need to support at certain SNR, and then from that you derive the spacing between the tones, and therefore the duration of the tones, to make sure that the Doppler is not an issue. Okay.
I think if I just think about what you were saying, you're basically saying that in OFDM you prepay for your lack of knowledge of the sample of the channel by putting in the cyclic prefix. That takes care of sort of the worst case or all plausible cases. In CDMA, you'd have to spin some spectrum to determine the nature of the channel in order to equalize it. So you both spin something based on what you don't know about the channel.
Yes and no. It's a little different. For instance, let's say there was no Doppler for now, right? You can make the cost in OFDM go to 0. So it's just some microseconds, but the symbol could be very large. So the fraction you're paying can really go down significantly.
Only if the channel's stationary during the symbol length.
During the symbol
Which
length.
is the same for CDMA. You can make a measurement of the channel and then use that measurement for a while.
True.
The same amount of time.
That is true. But a measurement of the channel will not give you the perfect channel in CDMA, right? In OFDM, it doesn't matter. You don't need to.
It doesn't matter. You're prepaying for the total cost.
No, but
could be.
But that prepayment in OFDM, so you can pay the same amount in CDMA. You still don't get. There's still mixing. In OFDM, by that prepayment, there is no
Specific
mixing.
knowledge to do the equalization, which you don't need in the OFDM.
OFDM. So it's
I understand.
the lack of knowledge there also costs you something. I'll tell you what it costs, but it's a little different cost.
You're saying orthogonality is preserved even if you don't know the channel, but you still have to pay dearly in OFDM for not knowing.
It's not dearly.
Because you waste your energy. I mean, in order to meet the SNR in all the sub-channels, you have to transmit a lot more power than you would otherwise have to in the channels that are strong. So
No, actually, the transmitter doesn't know what channels are strong typically, because it doesn't have any knowledge of this. What I'm saying is that I'm actually not saying at all what you said. I'm just talking about mixing of degrees of freedom at the receiver. That
You're doing delay spread, not.
yeah. So the degrees of freedom simply don't mix.
but you still lose by not knowing what the channel is even in OFDM.
No, that is completely equivalent. That is not any different between OFDM and CDMA or anything else. Okay, if you spread the energy uniformly across the band, not knowing the channel, every technology has the same capacity, right? But there's the subtle point I am trying to say is that in principle you can equalize CDMA, but you can only equalize to the extent you know the channel, and then therefore unmix them. But that's never going to be perfect. Once they mix, you can never perfectly unmix them. In OFDM, they never mix, and because that is not even relying on your knowledge of the channel. They just don't mix, and so you have perfect separation in a sense. Of course, perfect means 35 dB or whatever you want to design it for. Okay, but it's much easier in OFDM because you don't need the knowledge of the channel. Okay. So this knowledge of the channel, this channel model is actually good enough for point-to-point links. It's not good enough in multi-user mobile environment, right? And that it's because there is another component of the channel that is missing over here. There's another component of noise, the power of which depends on the power of the signal. Okay, so this is a better model of the channel. The fact that you can sit right next to the cell site and not see 90 dB SNR tells you that this alone cannot be the source of noise. There is another source of noise right here, which is proportional to the signal power. So the noise power is actually signal independent noise power plus signal proportional noise power. Okay, so this component we call self noise. Okay, and there are subtle reasons why this is important, and it changes things in subtle ways. So self noise, as I just argued, it's a fundamental property of wireless systems. You can't get rid of this noise. Even in OFDM, there will be certain, at some point there will be some noise. It's the energy that leaks out of your cyclic prefix will saturate what you can do. Okay. How is channel estimation done typically? If you're trying to estimate a certain number of parameters, you will have to spend a certain number of degrees of freedom estimating them. So typically in OFDM systems, you can just mark out a few of these boxes in which you transmit known quantities as opposed to sending any information. Since the quantity is known to the receiver can use that energy over there, the received energy, to actually, it knows the transmit energy, it knows the received energy, it can use that to make the make an estimation of the channel. Okay, this works in the conventional model where where you have to estimate the channel in the presence of noise that is signal independent. Okay, if there's signal dependent noise, then you need to not only estimate this noise power, but you also need to estimate this coefficient of proportionality, so to speak, right? So so you have to do something a little different than which we just saw in the estimation of the channel. So if you look at this channel model, which is a more complete channel model, which has a self-noise component, there's still a fading channel, and it really depends on whether edge fades or doesn't. So it's a fading channel. It could be a multipath channel. I'm not highlighting that aspect of it, but it's certainly covered. This channel is no different than the conventional additive noise channel for a point-to-point link, because if the link is point-to-point and the transmitter has certain power, and you know the power of this noise, then you might as well add it, and it doesn't appear any different. Anything you do for that channel can now be done for this channel. So once you fix the power of this, it practically behaves. So this is no different than the additive noise channel once you fix the power of the noise. But I'm making a tacit assumption here that the receiver I'm going to use for this model isn't any different than the receiver for an additive noise model. It has been shown that under the self-noise model, when the self-noise term dominates and the SNR saturates, the capacity still grows with power, but grows logarithmically with power. Okay. Now, as engineers, we know that if something grows logarithmically, you can write that off. That's not a gain worth going after. Okay. So the fact that the capacity goes logarithmically with power as engineers is actually not material. If you want to capture the logarithmic gain in power, you have to build a receiver that's a little different than the receiver you build for additive noise. So for all practical purposes, the capacity is not growing. So we're going to use the additive noise receivers, and even for receiving a signal in which there is a proportional component of noise. This model, however, is different than the additive noise model in a significant way when there is multi-user power allocation. Okay, so supposing there's a base station that talks to many users at the same time, multiplexes many users, and it must it has a certain power. It must allocate some fraction of the power for one user, some fraction of the power for the other user. Then this model has consequences. It's different than additive noise model. If noise is purely additive, then I can allocate power however I want. Okay. However, if there's a self-noise component of it, then I have to make sure that power I allocate to one user doesn't, if it's going to show up as interference to the other user, then the dynamic range of my power allocation will be very different than if noise was only fixed and independent of the signal. So once signal becomes noise, then I have to be careful in how much power I can put in various degrees of freedom, because now degrees of freedom are leaking into each other, and that limits what I can do. Another big difference is that this model is different from the fixed noise model in a significant way when the self-noise is cross-user, which again brings me to the CDMA versus OFDMA. Okay. In CDMA, let's say a transmitter is transmitting to two users. Okay. Now they're both using equalizers or whatever, but any energy I transmit to user A is going to become interference to user B in the form of self-noise, because user B cannot perfectly equalize the channel. Since it cannot perfectly equalize the channel, not only some of its, so I'm, let's say, sending signal A to user A and signal B to user B. If user B cannot perfectly equalize the channel, some of signal B will become noise to user B, but some of signal A will also become noise to signal B, because it cannot, it trying to equalize the channel. If it doesn't equalize the channel, user A's power will also show up in user B's signal. Right? Now, if user B happens to be very close to the cell site, but user A happens to be very far, I cannot really, in that case, I transmit a lot of energy to user A but very little to user B, because if I transmit very little to user B and sum of signal A's energy becomes noise, then I can wash out user B completely, right? So the fact that the self-noise term is cross-user in CDMA. Now this is the difference between OFDM and CDMA. In OFDMA, if I am transmitting different degrees of freedom to different users, right, the fact that a user may never estimate this channel correctly will still mean that whatever you receive will have some noise due to channel misestimation of the channel, because even in OFDM system you use a single tap equalizer. If you don't know the channel precisely, you'll get some noise, but that noise is only proportional to the power of signal transmitted to you, not the power of signal transmitted to somebody else, because the degrees of freedom don't mix. There may be self-noise on a certain degree of freedom because you didn't estimate the channel properly, but if you transmitted to user A on some degree of freedom and very high power, and user B on some other degree of freedom, since channel knowledge is not required to maintain that isolation, right, user A signal doesn't interfere with user B signal. User B still has a self-noise component, but it is only proportional to the power I am transmitting to user B. And if I am transmitting very little power to user B, that's okay. But if I, even when I'm transmitting a lot of power to user A, but in CDMA, the self-noise is also going to depend on the power I transmit to user A. So it's going to limit the dynamic range of power control that you can do. In data systems, we want to actually do a large dynamic range of power control because you want to spend less power or correspondingly give more data rate to close by users, even while you transmit large power to somebody else. Right? But if they start to interfere, then and you cannot equalize, then you lose that ability. So this is a subtle difference between CDMA and OFDMA, that the self-noise term becomes cross-user in CDMA, but self-noise term is always there if you cannot estimate channel, also in OFDM, but it only depends on the power to that user, not some higher power that you may be transmitting to somebody else. So that actually increases the dynamic range of operation of OFDM across different users. I think these slides probably say what I just said. So in CDMA, if you're transmitting two signals XA and XB at different powers, the total noise you will see, the self-noise term will have both the power of the total power you transmitted at the transmitter, which is power of A plus power of B, and for the receiver of XA at OFDM, the self-noise term only involves power of A. So if you transmit much more power to B, it will hurt you in CDMA, but it will be okay in OFDMA.
Because the frequencies are actually applied on the receiver.
Yeah, that orthogonality doesn't depend on that orthogonality doesn't depend on knowing the channel.
But if the front end of your preamp is nonlinear, that
will affect everything. That's true. But that limit is usually set a lot higher, right? Because you control that design. So SNR and self-noise. See, in the normal model of SNR, so self-noise also does one peculiar thing. Okay, if you transmitting certain power to a certain user, let's say you transmit certain power to somebody and they see 5 dB SNR, can you assume at the transmitter that if you transmit double the power to them, they will see 8 dB SNR? Well, if noise was independent of signal, you could say, well, in order for me to have higher SNR at that user, all I need to do is to double my power to that user. All of a sudden, that user will see 3 dB SNR. But that's the fixed noise model. In self-noise model, clearly that isn't the case. If I'm sitting right next to the cell and seeing 13 dB SNR, and you say I increase the power output of the cell by 10 dB, I'm not going to see 23, but I'm still going to see 13 dB. So when you're trying to allocate power at the transmitter to various users, it's actually important for the transmitter to know that if you put more power on a certain user, it's going to see benefit from that power. If that user is already saturated by its self-noise component, then you actually don't want to spend any more power on that user, right? So the right thing will be to give more power to those guys that are actually benefiting, whose SNR will go up if you give them more power, right? So clearly that distinction only holds in the self-noise model. In the fixed model, you assume that the thing will go up, and it may not be true. So, but however, you need one extra parameter to characterize the self-noise model. So this is the normal model of the channel SNR is this. As you increase the transmit power, the SNR increases. This is the line on which you operate because noise is fixed. In the self-noise model, there is a fixed component of noise that doesn't depend on the power received. So it doesn't, and there is a self-noise component that actually depends. It goes linearly with the power received. So the total aggregate noise you see is this, and this line does not pass through a zero, as or this line has a slope. This is your independent noise model. So this noise requires two parameters to characterize: this intercept and this slope. To characterize the noise in the fixed case, you only need the intercept because this slope is 90 degrees. Okay. So there's an additional parameter you need to know in order to make sensible decisions about how to allocate power in a multi-user environment. And for that, we introduce what we call null pilots, which are these blue dots. Of course, the picture shows them at the same density, but the null pilots typically, much less dense than the red pilots that are used to actually estimate the channel. Null pilots are symbols in which you transmit nothing. So every few symbols, let's say, a few symbols out of the total, you will transmit nothing. You transmit no energy. Clearly, if you receive any energy in the receiver at those points, that energy could not have been the result of self-noise because you didn't transmit anything. So there would be no self-noise on those symbols. Self-noise is proportional to what you transmit. Okay? So any noise that you see on the null pilots has to be signal-independent noise. It's a measure of the intercept. It's a measure of the noise that exists that is not dependent on the signal. Now you can measure noise on the regular pilots. That is the sum of the independent noise component and the proportional noise component. So making both those measurements actually characterizes the channel completely for you, and the transmitter can make more sensible decisions in allocating power. Okay. So there are many implications of the self-noise model to wireless systems. I'm not going to, you can, if you design it properly for self-noise, for data systems can benefit from that. I'm going to, so you can see higher capacities, but I'm going to pick a specific one, which is superposition coding, and describe how superposition coding behaves differently with the fixed noise model as with the self-noise model. Okay. So what is superposition coding? Superposition coding says that splitting the degrees of freedom. So when you're transmitting to users in very different conditions, let's say you're transmitting to users that have very high SNR because they're close to the cell site, and a user that may have very poor SNR because it's far from the cell site. Superposition coding says that it is actually not optimal to split the degrees of freedom. Say, this part of the bandwidth I'm going to put energy for the user that's far away, and this part of the bandwidth I'm going to put energy for the user that's close by and information for the user that's close by. You can do that, of course, and you get certain capacity, but you can get higher capacity, especially when the conditions are very different at the users, by actually putting energy for both users in all the degrees of freedom. So superposing one user's signal on another user's signal will actually give you gain, and the gain depends on how different the SNRs of the two users are. The more different the SNRs, the higher the gain. Then the less optimal it is to split the degrees of freedom across the users. So you can say that this rate curve actually tells you what you can do if you split the degrees of freedom, the rate you can allocate between various users, achievable rate curve. This is the one for superposition, and you can do higher rate to the users, higher capacity. The region is better if you actually put energy in all the degrees of freedom rather than splitting the degrees of freedom into orthogonal degrees of freedom. That's just from information theory. A lot of people here might be familiar with that. Okay, so how does superposition work? Supposing a user has really bad SNR. Okay, so noise is very high, signal energy is limited. Okay, clearly with bad SNR, you probably can't, let's say you're using QPSK constellation to communicate with this user. Now there is another user that has really good SNR. Okay? So one choice you have is carve out some degrees of freedom for this user and carve out some degrees of freedom for the other user and split your power across the degrees of freedom. The other choice you have is something different, superposition coding, where you transmit a 4-point constellation or QPSK constellation to the user with bad SNR. Okay? And on that constellation, you superpose another 4-point constellation. So this is actually not a valid point of the constellation. This is only for, but you superpose this constellation, which means you're actually, instead of transmitting this point, you're actually going to be transmitting one of these 4 points. Okay? Instead of transmitting this, you're going to be transmitting one of these 4. Okay? So you superpose this constellation on top of the constellation meant for the bad user, so to speak. Clearly, the bad user has very high noise. It has no ability to distinguish between these fine resolution points. So all it sees is a cloud of points here, a cloud of points here, a cloud of points here, a cloud of points here. If it receives something in this cloud, it says it receives this point. If it receives something in this cloud, it says it receives this point. This signal is also seen by the close by user that has high SNR. Of course, that user has the ability to resolve more finely these points. So it will ignore basically which cloud you sent, because that information is meant for the other user. It will just pick on which point you sent. Okay? So this way what happens is you're using your bandwidth twice in a sense. You're transmitting to the poor SNR user, and you're on the same bandwidth superposing a constellation transmitting at the same time to a close by user. So you're reusing bandwidth, so to speak. There's a lot of emphasis people pay to reusing bandwidth. The whole MIMO system is an attempt to create more bandwidth out of fewer degrees of freedom by exploiting multiple antennas or other dimensions to get more bandwidth, right? But this to me is a low-hanging fruit in the system, right? You can actually get gains just by superposing things and actually increasing bandwidth, so to speak. And the gains, as I said, are proportional to or depend upon how different the users are. So if one sitting in really bad SNR, one sitting in really high SNR, you can effectively reuse the bandwidth twice without additional cost. So how do you typically decode this? Joint decoding is typically complex, and so you do successive decoding. The guy close by, which is high SNR, basically the guy far off doesn't do anything different. It just does its normal decoding. It just picks which quadrant you're in and makes decisions based on that. Okay. The guy close by actually translates all points to 0 and sees the fine constellation and only makes decisions on that, right? So this is effectively what that says. So this all works. Remember, the gains are more when the SNRs are different. But another thing happens when the SNRs are different. What if there is self noise? Right? So then things look, with self noise the cancellation is imperfect. So it actually reduces your gain significantly. I'll show you that. So let me just go, maybe this can show it better. So these are your constellation points that you actually transmit. This was the intended transmission to the bad user. This is the intended transmission to the good user, and you superpose them, and these are the points you actually end up transmitting. And let's see what the next slide. Okay. Now the way you decode, the good user decodes is it estimates the channel and basically then cancels this point out, and then you're only left with the 4-point constellation at the origin, then you decode based on that. However, now you see the self noise seen by the good user actually depends on the power of the signal you transmitted to the bad user. So even if there's a little bit of that, right, and there's a little bit of misestimation, then it impairs your ability to detect this finer constellation significantly, and that impairment is proportional to the larger power you're transmitting, right? But the gain is also was theoretically more if the power difference was larger, but the impairment is also higher in the same conditions, so to speak. So let me just take another detour and I'll come back to this. Okay, another lesson unlearned, that QPSK is the right constellation for low rate wireless communication, because everybody uses QPSK, And there's a reason everybody uses QPSK is because there's a legacy reason. The real reason has actually long disappeared, but the legacy is continued, right? So the question is QPSK the best constellation to use? Well, information theory says that any constellation you use to communicate, its marginal distribution should look Gaussian, right? The marginal distribution of any constellation you use should look Gaussian. QPSK doesn't look Gaussian, it's like this, right? It has weights on these two distinct points. If you, in addition to QPSK, you add a point at 0, so the QPSK is 4 points, you add a point at 0, and you use that with higher probability that you use any of the 4 points, then you can easily create a marginal like that using a 5-point constellation instead of 4-point constellation, where the middle points actually used more frequently than the 4 outer points. You create a marginal like this. This marginal is actually a better fit with the Gaussian than that one, and you can say that it actually improves the capacity of the channel a little bit. Very slight, 0.2 of a dB or something, but it does. So capacity calculations support the idea that you actually use this marginal, which means you use a 5-point constellation instead of 4-point constellation with a point in the center of the 4 points, and use that point with higher probability than the 4 points. Okay, so that's a 5-point constellation. If you use this point more often than the others, then you can create that marginal distribution with the center weight being higher, and the capacity is actually higher. But I'm going to do something more radical. Okay, I'm going to say that I'm going to use the center point 4 times more than any of the other points put together. So out of every 4 symbols, I will transmit 3 zero symbols and 1 non-zero symbol, and the non-zero symbol could be any one of the 4 points. Okay, so now I'm trying to do something extreme. I'm not just trying to put more weight at the center, I'm trying to put huge weight at the center. Of course, if I put the right amount of weight, I actually gain over QPSK. If I put this kind of weight, I don't actually, we can show that the performance of this system actually is a wash. It performs exactly the same as QPSK. Okay, but I'll go through the exercise nonetheless of showing you what to do. So for every 4 points you transmit, 3 of them are going to be 0, 1 of them is going to be non-zero, and the non-zero point could be any 4 of the regular QPSK constellation points. So how do you carry information? Well, the 2 bits carried in the fact that the position of the non-zero point within the 4 carries 2 bits, and then the additional 2 bits is carried by fixing which constellation was transmitted, and then you can put further coding on it and code it to whatever rate you want, some low rate if you wanted to code it to. So it turns out that for coding it like 1/6 or something like that, the performance is the same as performance of QPSK. The way you will decode is you'll first try to decode which the non-zero symbol is, and then you will try to figure out which point was transmitted with the non-zero symbol. So this is just another way of communicating with 5 points instead of 4 in such a manner that the 0th point is used much more often than the non-zero points. Okay.
But your 4 symbols are essentially carrying only 4 bits, while 4 QPSK symbol are carrying 8 bits.
No, but then you will code it down. So let's say you wanted to. So
this is more resilient to.
At the end of the day, let's say you wanted to carry 1 bit every 8 symbols. You can code this to carry 1 bit, and you can code QPSK. It turns out the performance is similar. Okay. Okay. So this is how you can do a soft decoder for this. First you decode on position and then you do bits, and the performance does turn out to be similar to doing the right codes in QPSK. Okay, so the big question, so what? I mean,
Rajiv, make sure I understand. You're saying for a given SNR, the capacity of that channel, that 5-symbol channel, is the same as the capacity of QPSK?
Similar. I'm not saying exactly the same. If you use the 5 symbols optimally with the right probabilities, it's higher from a capacity point of view. But if I put like a 75% probability of using the 0 symbol, then for like 1/6 kind of coding rates, it's about the same. So it's very close. Okay, so it's just another way of doing it. So the thing is, so what? I mean, so you could have something very straightforward using QPSK, but you were a little more convoluted about doing things, but you got the same performance. So what's the big deal? Why not just use QPSK? Okay, Okay. One reason. So for the regular model, fixed noise, everything works. You could use one or the other, it's the same performance. However, if you have self-noise, the things are different. Remember, self-noise is proportional to the power transmitted on a symbol. If you transmit no energy on a symbol, which is 75% of the points being 0, 75% of the points have no self-noise on it. Right? If you didn't transmit anything, there is no self-noise on that symbol because it's proportional to the power of the symbol you transmitted. Okay? So on 0 symbols, if you superpose a denser constellation, so small power compared to the other guy, for the close-by user, the close-by user doesn't see any self-noise from the other users. But you use the bandwidth to communicate with the other user nonetheless. Right? So the two techniques are not significantly different for fixed noise, but when you have self-noise, they're actually, so this just shows you that when you have the self-noise model leads to different results and different ways of looking at things and different optimal conditions than the fixed noise model. In the presence of self-noise, clearly this is much more advantageous. Now, on 3/4 of your spectrum, you can communicate with the close-by user without any penalty of self-noise coming from the power you're transmitting to the power of user. Because when you transmit on the non-zero point, you may also, we don't know what the optimal is. We haven't proved any theorems here, but this is just a demonstration that to show that this works better. Optimal under self-noise is actually usually much harder to compute, and I haven't done it. But it clearly shows to you that in any practical situation, you can do better under self-noise by doing superposition slightly differently than you conventionally do superposition. It's also similar to Decode, by the way. It's very trivial to decode this because you're not trying to, for this guy, it's really simple to decode. On the 0 symbols, you don't see anything. If you see large energy, you just ignore the point. So I come back to the fact that OFDM is a physical layer technology, and I'll give you some examples as to why signaling on tones actually advantageous in other ways than just communicating data across users. So there are many other examples which I will not go into detail, but I'll take a specific example here. But OFDM partitions the resource much more granularly than the other technologies, and it's actually better for MAC layer design, for QoS, for lower delays, and all those things. But let's leave that on the side. I'm going to take one specific example of something we call flash signals for cell identification. Now, many of you may have heard of Sergio Verdu. He was actually on the technical advisory board of Flarion Technologies, and he came for one technical advisory board meeting, and he said, I've been looking at this communication in the low SNR regime, very low SNR regime, and I've come up with the signals that are optimal for communication in the low SNR regime. And I know that you call your technology Flash OFDM, so I should have picked a different name. But because of the nature of these signals, I call them flash signals. Okay. So he described to me what they were, and I told him, Sergio, we actually use these signals in Flash OFDM. We actually have, at that point, I had no recollection of why we called Flash OFDM, but I told him that day he gave us the reason as to why we call Flash OFDM. Because he came up with these signals called flash signals, and we were using them. So that's a justification of why it was Flash OFDM. So I'll describe to you what flash signals are, and why they're called flash signals will be obvious, and how we can use that for other purposes, and how having OFDM therefore is better than other things. So what is a flash signal? So in OFDM, the resource is divided in time and frequency. So each box represented one single tone over a single symbol duration. Right? So what if you concentrate a lot of power on 1 degree of freedom? Let's say, I'll use the term 26 dB because that's what we do. But let's say you have some average power you're transmitting all the degrees of freedom. But in one specific degree of freedom, you put 26 dB higher than average, which is 400 times higher than average. Okay, and you do this roughly to 1 in 10 to the 5 degrees of freedom. It's not, you're not using this for communication in the normal way. But this, so most of the time you see signals with regular power, small power, and every once in a while there'll be a flash, really high powered symbol will show up for a very small duration, because the density of such symbols is 10 to the minus 5. So as an aggregate, they hardly consume any power. It's 400 times higher power than normal, but the density is 10 to the minus 5. So the total power spent on flash signals is negligible. The total resource spent is negligible. It's 10 to the minus 5 of your total resource, which is also negligible. However, you can see why the flash signals are called flash signals. It's a massive jolt of power in one symbol. Now, what is 26 dB? Okay, why 26? I'll give you. So let's say you were transmitting, you were observing noise, a Gaussian signal, right? And so Gaussian noise, you were observing your various degrees of freedom, and the variation in power you observe, right? It's a Gaussian variation. That's why it's called a Gaussian signal. So let's say you observe a certain power x in one symbol, you may observe 0.3x in the next symbol or 1.4x in the next symbol. What's the probability you will observe 400x in any symbol? It's virtually impossible in a Gaussian distribution. The probability less than 10 to the minus 50 or something like that under a Gaussian distribution to see 400 times the average power on a single degree of freedom. You can make that calculation. That's why the distribution is Gaussian. It tails off very, very quickly. It's an exponential decay. To see an outlier of that magnitude is going to be a very low probability event. Okay. So if you're observing something and all of a sudden you see high power, you can be very sure that was really not the outcome of a random process. That if you saw that power, somebody put it there. Okay. So you can actually use it to communicate. Of course, these are very few bits on very few symbols, so you're not communicating high-speed data by doing so. However, remember that wireless systems do a lot more than just communicate high-speed data. So one of the things they do is, when you turn your cell phone on, one of the first things it does is it scans the spectrum to see where there is service. Let's say if you have a CDMA cell phone, what does it do? It goes to some band. So it may anticipate in some 15 megahertz band that the operator owns that there may be service somewhere. It doesn't know where. So it goes to some part of the band and starts looking. And then if it doesn't find it, it goes a little bit off on frequency and keeps looking. It just moves a little bit and keeps looking. And how does it look? It has a long sequence, right? And the cell is transmitting some sequence, which is also very long. And it must correlate what it's observing to all different rotations of this long sequence, a quarter chip at a time, to see where there is alignment. And once it finds alignment, it knows that there is service here, and that it can also therefore discover the identity of the cell that's providing the service. But a priori, it has no notion of it doesn't have frequency sync yet. So its crystal may be vibrating a little off the actual frequency. So it must do this in small steps because it anticipates that its crystal may not be perfect, and it knows what range its crystal is, plus minus how many ppm. So it must do these things, repeated things. So it's a very convoluted process. When it's a dedicated hardware, it does it in a few seconds, I guess. But when you turn on, and mostly it anticipates where the service is, but if it doesn't know, if you go from one country to the other, sometimes it could take a long time just figuring out which band the service might be in, and within a 15 megahertz band where exactly it is located. And every place it must do this whole correlation across everything. Okay. So it's one way to do it, but imagine that you use flash signals. Okay. So every base station transmits pilots for regular communication, but also transmits these flash beacons every now and then. Very low density, 10 to the minus 5, okay, with very high power. Now anybody's going through the spectrum, just doing regular FFTs, no big calculation, just keeping tag of what you see on each thing. Every time you see a degree of freedom that's significantly higher than the average you're seeing in your FFT, you know that that's a flash signal, right? The amazing thing about, because it's tones you're transmitting, it's eigenfunctions, is that you can pick up flash signals without having timing sync with the signal you're trying to detect or frequency sync. The majority of the signal will still, the energy of the thing will still show up in one of the degrees of freedom that you do. And you can pick it up So very little calculation is required to. So if you quickly wanted to say where there's service, and there may be carrier may be anywhere, so you go to some 1.25 megahertz. A flash signal occurs every few milliseconds, 100 milliseconds, 90 milliseconds. So you wait 90 milliseconds. If you didn't find any flash, you move another 1.25 megahertz. So you can just, in a fraction of a second, you could be done with large amount of spectrum and know whether there's service or not. And this, if you detect a flash signal, it'll give you the frame and level timing right away. And then you, with very little, because now you know big coarse timing, you can get fine timing very easily just by correlating inside, right? So a lot of other things that of course we do the CDMA, but are done with huge amount of calculation, are just very trivial, just because you're using eigenbases for communication, and that's special in nature. And the reason you can do it, detect flash signals without ever getting a frequency or a timing sync with the source, is because they're eigenbases of a linear system, and you really don't need timing, and you just do regular FFTs. One of the coefficients will show up with large energy.
May I ask you something?
Sure.
So this is when you do IFFT. This is a high power component in the frequency domain.
Mm-hmm.
I'm asking that because of the peak to average power ratio. Does it have any effect if you're putting the high power?
Well, so think of what you're transmitting when you transmit a high-powered signal tone. You're transmitting a sinusoid.
Yes.
It's the best peak to average signal that you can transmit. Nothing gets better than transmitting a sinusoid, right? That's like transmitting a pure carrier. In fact, this signal is so good from peak to average standpoint that normally we can actually transmit 1 watt from the amplifier the time that you're transmitting this signal, this flash signal. Regularly, if you transmit 200 milliwatts, you can actually easily transmit 6 dB high power, because the peak to average power ratio of this signal is as good as it gets. It's like a carrier, right? So they actually allows you to transmit beacons more powerful than you can otherwise transmit. So they can get higher penetration because you can transmit a higher power with the same amplifier.
But that must be the reason that limits you to 26 dB, right? Part of it.
No, it doesn't. That 26 dB is design, and I'll tell you how we arrived at 26 dB. We had roughly 100 tones per symbol.
Right.
So we took all the power and put it on one symbol. That's a factor of 100, which is 20 dB. But since this is a sinusoidal signal, we can boost the power in that for say 6 dB, so it gets to 26 dB. Yeah.
Okay. Yes.
Right.
Exactly.
So we want to transmit the highest power, because the beacons should have the highest reach, because you can detect these beacons even where you can't see the pilot yet, or you don't even know how to find the pilot, because with 6 dB higher power they penetrate better.
And essentially the location of the tone will give you identification of
Location of the cones gives you an identity of the basis. So it solves a lot of the problems for you, right? So it's just simple. What we do is a little more refined than that, but I'm just giving you an example as to how things that are very convoluted when you don't use eigenbases are really trivial and simple when you do use them.
You say you put all the power into just one tone.
Mm-hmm.
You transmit 0 power in the other tone?
Yeah, it's just few degrees of freedom, yeah. It doesn't happen very often. It happens very rarely. You can actually transmit something, but we actually don't transmit 0. We'll transmit something else. We transmit a small signal that's higher bandwidth, so that you can get your fine timing on that symbol right there as well.
I see.
But we can transmit higher powers also. So you see the benefit here. It was just to show you that there are other advantages that you can, and this flash signal can be used in many ways. You can do inter-carrier handoff with this, and you can insert flash signals from one carrier into another carrier, because it doesn't take any bandwidth or something. So when you're just monitoring that carrier, you can actually see what's going on in a neighboring carrier, because that transmitter is inserting beacons into your carrier without interfering. So these don't represent any interference. The total power, fractional power you spend on flash signals is 10 to the minus 5 times 400, which is very, very small. So there's no interference. There's no bandwidth cost, because the degrees of freedom are very, very small that you spend on these. But you get a lot of other system benefits by broadcasting this information.
What's the information theory basis for that? This is the most optimum type of signal in like you mentioned.
So for non-coherent channels in low SNR, you can see why this would be most optimal, right? Because if you spread the signal in any other way, degrees of freedom, you have to estimate the channel. You spend most of your energy estimating the channel. This shows up on a single degree of freedom, right? So it actually the Sergio proved that was the optimal way of doing from an information theory point of view. Okay. So another just related example, this I use this because I think it's specifically good in a university environment to know the difference between the real world and the academic world. So this is just describing the beacon. Let me just go to that slide. So this also, I guess I skipped over the slides. So you can see that the density is really low. This is actually higher than the flash density you will see. So you see why the signals are called flash signals. I guess we covered this. You can cell ID, sector ID, a lot of stuff can be. And the best thing is that without even having synced your crystal yet with anything or done anything, you can pick these up. You don't even have coarse timing. You have nothing. You're just observing and doing FFTs, and you can pick up cell IDs and your frame timing and everything right there.
I thought that in an OFDM system, first you acquire that symbol timing and then only you do the FFT, right?
Pardon me?
In OFDM.
For regular communication. But if you're trying to direct beacons, you don't need to do that.
You can just take the FFT with that timing.
You just do regular FFTs. You don't know the timing. You should just try out the box, take FFTs, and monitor the average power and see if any symbol exceeds the average power by a factor of 20, because it doesn't happen in Gaussian. Pardon me?
I guess
You're not interested in data right now. You're just acquiring system. You just turned on and you're trying to see where you are, what service is available. You have no data going on yet. So you don't have any timing for any data yet. This could also be used for handoff in identifying other cells, right? So when you're communicating with one cell, and let's say it's an asynchronous system, there's another cell. You can pick up the beacons from the other cell way before you can actually detect the pilots of it. So you can monitor the strengths. You know when it's time to do handoff. This is when you go from one area to the other. You can do handoffs based on these signals. You can do inter-carrier handoffs based on this, because you can have one carrier inject beacons into another carrier. And then you can monitor the strength of this carrier by seeing the beacons in the carrier you're currently listening to. And so the other carrier is actually now much better for me because its beacons show up much higher than my beacons. You can jump to another carrier. So you can do lots of things. And in flash OFDM system, we actually do a lot of those things. But these are just the secondary benefits of doing this. Now, one important point.
Injecting those beacons into the next carrier does require you to have a much wider bandwidth in the transmitter, doesn't it?
Yeah, but transmitters typically have wide bandwidth. Adjacent carriers.
Enough to cover all the carriers.
Sure, yeah, transmitters typically have that bandwidth.
Okay, you're talking
yeah.
about 1.25 megahertz carriers. Okay.
No, even otherwise, there is no filter in the transmitter that actually, if you wanted to limit the transmit filter to 5 megahertz, it would be very hard.
That's right. Yeah.
Right?
Yeah.
Because transmitters typically have 100 megahertz.
20, 40 megahertz carriers already, you know.
No, but typically, if you have 15 megahertz of spectrum, the 3-5 megahertz you can still use to inject beacons into the other. Okay. So beacon interference. So this is an example that I like to cover at universities. Now, there is one issue. It really. So let's say you were designing some coders and decoders. How do you typically design a decoder? Let's say you were designing a decoder to receive a QPSK signal normalized to plus minus 1, or BPSK signal normalized to plus minus 1. If you receive a 0, then you say, well, I'm not sure about this signal, whether it was plus 1 transmitted or minus 1 transmitted, because I received a 0. So your soft metric says, you have no information on this symbol. However, if you receive a 0.9, you say the probability that A1 was transmitted is now much higher than probability of minus 1 being transmitted. Okay, so you assign some probability. And if you receive minus 1.1, you can say minus 1 was transmitted higher probability than 1. What if you're doing this and all of a sudden you receive 100? What do you do? If you're expecting plus minus 1, 100 shows up. Under the Gaussian noise model, you can bet your life that 1 was transmitted, because the probability of getting 100 from a 1 compared to probability of getting 100 from minus 1 is really, really high. Right? So you're expecting plus minus 1, 100 shows up, and you designed your system for Gaussian noise, you can say, oh, I can bet my life that plus 1 was transmitted. In reality, what happens? You say, I have no clue what was transmitted. I got hit by impulse noise, and I have no idea what was transmitted. Because that outcome is so unlikely under Gaussian noise But obviously it couldn't be the result of Gaussian noise affecting the system. It's probably the result of some impulse noise affecting the system. So just to tell you, when you design decoders, you should take that into account, right, in the real world. The fact that you can be, so in our case it actually happens. You get hit by an impulse from a flash signal, you don't want to make an error. Any code would make an error if the decoder wasn't designed properly. If the decoder was designed expecting Gaussian noise and saw that, you'll at once you can make an error, because if you saw 99, you would say it was definitely 1, and if that symbol actually happened to be -1, you'd make an error right there, right? So that just tells you that you have to do things, you have to use these models carefully, okay? Because it's only a model, and you have to also entertain the fact that the model could be wrong with certain probability, and you don't want to make an error when that happens, right? So in the Gaussian noise model, the metric keeps increasing. Your certainty over 1, as you see something larger and larger, keeps going up, and -1 similarly as you go in the other direction, right? In the real world, you have to, if you start seeing very large values, you have to question whether that's the right metric or not. Under Gaussian noise, it's the right metric, okay? But maybe a better thing to do is, after a certain amount, you just saturate this metric, saying no matter what I observe in any one symbol, I will never be totally convinced that whether what was transmitted was +1 or -1. I'll look at the code and then decide. This is a better thing to do, because with some probability your model could be wrong, and then you don't want to make an error. Okay? And doing so actually usually does not affect your Gaussian performance, because you typically do it in a regime which you don't even see under Gaussian noise. You'll never actually see 100 under Gaussian noise. So if you change the metric over there, your Gaussian performance is not affected at all, right? So one thing to do it, and this should be done irrespective of whether you're using flash signals or not, is that the way you construct your metrics should never be what Gaussian theory tells you. So you should actually always saturate the metrics, or even reverse them. You say something, I see something very high, I'm no longer sure, my metric is 0, I'm no longer sure whether it's a +1 or -1. So if you see a 99 and you're expecting +1, you might as well say I'm not sure anymore as to what it was, right? I'm actually, if you see something that high, actually you're now unsure whether it was 1 -1. If you see 5, maybe you say 1 is still a little more likely than -1. If you saw 100, now you've completely lost what was going on in your signal. And even if you did this, you reverse the metric, you're reversing in a regime where it should not affect Gaussian performance, right? So if you say, whenever I say something above 5, I'll say I don't know what I saw, I cause an erasure actually, right? But the probability of seeing under 5 under Gaussian noise is so low that it's actually not affecting anything. However, when your model becomes wrong, when you get hit by impulse noise or something happens, which always happens with a certain probability, because Gaussian noise is just a model, and you always have to entertain that other things can happen, that your modeling may not be perfect, it always pays to design decoders in which the metrics are such that you don't get penalized unduly if something unexpected happens. So it's always good to use this. And the reason I'm saying is we were already using this. So when we introduced flash signals in this, nothing had to change. Because what happens is, if you have this metric and you get hit by impulse, you cause an erasure on that symbol versus causing an error. Erasure is completely benign, because if you lose one symbol, actually beacons for the same power actually is less interfering than Gaussian noise, because they actually cause erasures in a symbol. And if you cause erasure in the symbol, you'll actually want all your power to be concentrated on that symbol, because once you cause an erasure, it doesn't matter whether it was 10,000 times more power than the symbol or 100,000 more power than the symbol. Erasure is an erasure. So you want all your noise to be actually concentrated in few symbols, because then you just erase a few symbols and you're done. It doesn't generally affect any other symbol. So this is just an example, just specifically in a university environment, to show you that when you design systems for the real world, you always have to make changes over what you learn in the academic environment, and those changes are based on the fact that when people in the academic world, they live by the models, they do everything for the model. They don't usually entertain the fact that the model is only right with some probability, and with some probability it may not actually be what you're looking for. So that's an important thing to keep in mind.
In your flash OFDM system, are the base stations all time synchronized, or
No, they're not.
required?
They're not.
They're not.
We did not want reliance on GPS. We want indoor deployment, dense deployment. So they're completely async. And the way we do handoffs is not therefore through flash signals.
Okay.
So
But what level of frequency synchronization do you require?
None. They were all independent, whatever,
Okay.
1 ppm crystals or whatever the crystals gave you at the base station. There is no level of frequency synchronization. We have a spec on the crystal. You can't use 10 ppm crystals in the base station. You can, then we have to design the system accordingly. But the cost of between 10 and is not material to the base station, so 1 ppm is fine.
Okay.
But we don't require any additional sync on top of that. So I mentioned many things that we unlearned in the process of designing Flash FDM. But there are 3 other things in addition to what I talked about that we unlearned. And this is they're actually not mine. They come from Tom. And he specifically asked me to put it at the end of every presentation. This is Tom Richardson. So I'm going to tell you 3 more things that we unlearned. We unlearned that the world welcomes technological improvement. Actually, the world resists technology improvement like you wouldn't believe it, right? All the people with current interests and power over you really resist everything that you do, okay? So world does not welcome technological improvement. Oh, there were 2, okay. That's the second thing we unlearned. If you join a wireless startup, you have a good chance of getting rich. We had to unlearn that. I think that was it, yeah.
Does Gaussian model that your chance of getting rich?
No, it's actually an impulse noise. Okay, thanks.